Welcome to the deep dive. We're trying to cut through all the noise, the complexity of these really dense technical docs.
Yeah, bring you the stuff you actually need.
Exactly. And today, we are plunging right into, well, the engine room of modern data management.
Mm-hmm.
We're looking at the capabilities in the Nutanix Certified Professional Database curriculum. So, NCP-DB.
Mm-hmm.
Basically, the core functions of NDB, the database service.
That's right. And look, our mission here, it isn't to just read you a study guide or something. We want to pull out the fundamental ideas, right?
Yeah.
How do you manage these huge, always-on database environments? We'll look at how this platform handles, provisioning, patching, protection.
The big three. The stuff that gives DBAs headaches all the time.
Pretty much, yeah. Worldwide.
And, okay, for context, we know this stuff is key for, getting certified. It's the logic behind those, 75 questions in 2 hours?
Yep, that's the exam format.
But we want to go deeper, right? Understand the why. Why these tools? We're trying to uncover those, mechanical secrets that really change the game for DBAs. The cost, the time.
Exactly. We want to show you why certain things were chosen, like why Petroni for high availability, and how that directly translates into, guaranteed SLAs for the business.
Love it. Making complex database stuff simpler and faster. Okay, let's unpack this.
Let's do it.
So, we have to start with that classic friction point, right? Everyone always needs copies of production data. Dev, test, reporting.
Always. The demand is endless.
And speed is everything.
It really is. I mean, traditionally, getting a big dev instance ready, that meant long copy times, moving data around, heating the production source with I/O.
Right, impacting performance.
Exactly. So a modern platform, its goal has to be giving developers instant access to data, but crucially, without messing with the live business systems.
Okay, so how does NDB do that? How do you get these fresh, full database copies, instantly? At any specific point in time, without waiting hours for data to move? What's the magic?
Well, the magic, or the core feature, is called Time Machine.
Time Machine?
Okay, Time Machine is really the heart of the data protection and management side. But here's the key technical bit. When it makes a clone or a snapshot, it's not actually copying all the data blocks right then and there.
Oh, okay.
It's really a metadata-only operation. It just captures pointers to where the data lives at that exact moment.
So wait, if I'm getting this right, the reason it feels instant is because the clone is just a smart set of pointers to the original data blocks. It's sharing the storage until the clone starts changing things itself.
Precisely. That's it. It changes the whole timeline from hours down to literally seconds.
Wow, okay.
It's more of an intellectual shortcut, you could say, not a physical copy effort up front.
Okay, that makes sense.
Yeah.
But that leads to the next obvious question, right? If I make, say, 10 of these instant clones from a 10 terabyte production database, I haven't physically copied 100 terabytes, you said. But those clones still need somewhere to write their changes, right, as they diverge from the original.
Yep, they absolutely do. And that takes us right into storage efficiency.
This is where it gets really interesting, I think. How does the system handle that? Because if I just made 10 clones, even if they start small, my storage admin is going to be knocking on my door pretty quick if I'm not careful.
Right, and that's where the system leans heavily on thin provisioning.
Thin provisioning, okay.
Think of it as optimization specifically for managing these shared copies. When you create that clone, you're not pre-allocating the full 10 terabytes of space for it. Instead, storage only gets allocated bit by bit as data actually changes within that clone. It's thin because it only takes what it needs when it needs it.
Okay, that's a massive win for efficiency. Huge. But let me put my risk manager hat on for a second.
Go for it.
If every clone is thin provisioned, they're all sharing that underlying storage pool. Isn't there a hidden risk there? If I overcommit that shared storage, couldn't things grind to a halt? Performance issues? Maybe even outages if the pool actually runs dry.
You've hit on a key point. It absolutely introduces a, let's say, management responsibility.
Right.
Thin provisioning relies on good monitoring. The system handles the efficiency. It does that perfectly. But you, the admin, you still need to watch the utilization of that underlying storage container.
Okay.
Because if too many of those thin clones start writing a lot of unique data, diverging heavily from the source, that shared storage pool will get consumed fast. The platform gives you the tool, but you still need to manage the overall consumption. Use those central reporting tools.
Excellent point. It's a tool, not magic. There's always a trade-off, or at least a responsibility.
Exactly.
Okay, so we've got speed with Time Machine, space efficiency with thin provisioning. Let's pivot to the ultimate guarantee, recovery, the non-negotiable part.
Right. If provisioning speed is critical, guaranteed recovery time is, well, everything. How does the platform actually connect our data protection policy to a specific recovery point objective, an RPO?
Okay, so RPO, that's the maximum data loss you can tolerate, right, in a disaster scenario.
Yeah. That RPO is directly governed by how often you capture the transaction logs. So if a customer says, we need an RPO of 5 minutes, meaning they cannot lose more than 5 minutes of data, then the log catch-up interval in the system, that's the frequency it processes and saves those transaction logs, must be set to 5 minutes. Or less, obviously.
Okay, that directly links the policy setting to the RPO promise. Makes sense. But there's this nuance in the policies that I know trips people up sometimes.
Yeah. The difference between snapshots and continuous log?
Exactly. Let's say my policy has continuous log retention set for, 7 days. But it also has daily snapshot retention set for 14 days. How far back can I actually restore to any specific second? Is it 7 days or 14?
It's strictly limited by the continuous log retention. So 7 days in your example.
Only 7 days. Okay.
This is super critical to understand. Those daily snapshots, they give you a solid recovery point once a day, going back 14 days. That's good. But that really granular point-in-time recovery, the ability to say, get me the database exactly as it was at 10:47 a.m. last Tuesday, that completely depends on how far back those continuous logs go. So 7 days.
Okay, 7 days of continuous logging.
Yeah.
That sounds like a pretty significant commitment, resource-wise. Storage, processing power to keep ingesting those logs.
Oh, it is.
It's a fundamental trade-off then, isn't it?
Yeah.
The farther back you guarantee that super granular recovery, the more you pay in terms of, storage tax.
Absolutely. That decision, should we keep continuous logs for 7 days or maybe just 3?
Yeah.
It's often an economic one.
Right.
You're balancing the business risk of data loss against the real operational cost of storing and managing potentially huge volumes of transaction logs. It's expensive, yeah, but often those strict SLAs demand it.
That's a perfect segue, actually. We've covered getting data ready and protecting it. But, like you said, recovery guarantees don't mean much if the database isn't even running.
True. Availability is key.
So let's pivot hard now. Let's talk high availability, HA, and keeping things consistent. For running HA open source databases, specifically PostgreSQL, what's the main component doing the orchestration? Managing node health, handling failover automatically.
Right. For an HA PostgreSQL cluster managed within NDB, the key player there is Patroni.
Patroni, okay, I've heard of that.
Yeah, it's a well-known open source solution. What it does really well is abstract away all the complexity of PostgreSQL's streaming replication. Think of it as the intelligent watchdog for the cluster.
Good watchdog, I like that.
It's constantly monitoring the cluster state, checking the health of the primary node, standby nodes, and crucially, it handles the automatic, safe election of a new primary if the old one fails.
So Patroni basically gets rid of all that painful custom scripting and manual intervention people used to have to do to keep PostgreSQL clusters highly available.
Pretty much, yeah. It handles the orchestration behind the scenes. It makes sure that primary standby relationship is always maintained automatically.
So why Patroni? Why is it generally preferred over maybe older ways of doing clustering in this kind of environment?
Well, a big reason is that it manages the cluster configurations centrally. It uses something called a distributed consensus store, like etc. or console, and that gives it much greater reliability and consistency, especially when things change in the cluster compared to older tools that might just react to resource availability. Patroni knows the desired state, and if a node goes weird, it actively enforces failover and recovery to get back to that state. It's active management, not just monitoring.
Got it, active management. Okay, so Patroni keeps the lights on for HA Postgres. Now, what about keeping the actual database software consistent and updated? Patching? Yeah. That task people used to dread.
The weekend of doom, yeah.
Exactly. Especially complex things like, say, a SQL Server cumulative update, a CU. You need to push that out to dozens of instances quickly and make sure they all get the exact same update. How do you ensure that uniformity?
That consistency, that uniformity, that's defined and enforced by the software profile.
Software profile.
Yeah. Think of it like the golden image or maybe the master blueprint for your database software stack.
Okay.
It defines the exact database version, the OS compatibility, and crucially, the patch level. That includes all the CUs, security patches, everything.
So that's the real power, isn't it? It abstracts the nitty-gritty away from the DBA. They just manage the desired state of the database engine itself.
Precisely.
So when a new SQL Server CU drops, you update the software profile once, You test that, and you just tell the system to apply that known good state everywhere. No manual errors.
Absolutely. It turns what could be a multi-day, error-prone patching nightmare into a repeatable, profile-driven, automated task.
Yep.
The system guarantees that every instance using that profile is identical. It kills configuration drift.
Fantastic. Okay, sticking with system management. When it's time to upgrade the actual NDB system software itself, the platform running the databases, what's generally seen as the simplest, most reliable way to do that infrastructure upgrade.
Right. For upgrading the underlying components, the NDB software itself, maybe the hypervisor, firmware, that sort of thing, the easiest and most reliable path is using Nutanix LCM, Lifecycle Manager.
LCM.
LCM basically automates that whole upgrade process across all the Nutanix cluster components. It handles dependency checks, version compatibility. Its whole job is to minimize disruption and make sure the system update is smooth.
Automation again.
Yeah.
Clearly the cornerstone here. Okay, let's shift focus a bit to management visibility. Say I'm running, dozens of databases, maybe across multiple physical Nutanix clusters.
Common scenario.
And I need that single source of truth for long-term historical trends, like tracking storage growth over the last 6 months or maybe CPU usage across everything. Where do I go for that big picture?
For that centralized, long-term view monitoring, analytics, historical data across multiple clusters, you absolutely need to be using Prism Central.
Prism Central, not Prism Element.
Right. Prism Element is great for managing a single Nutanix cluster, but Prism Central is the real single pane of glass for the whole enterprise, potentially spanning many clusters.
Oh, okay.
It aggregates all the performance data, the utilization trends, alerts, everything from all the clusters it manages. It's essential for things like capacity planning at scale.
So if I need to build that report for my boss showing total database storage growth company-wide over the last year, Prism Central is the tool.
Exactly. It gives you that macro view, that cross-cluster context that Prism Element just doesn't have by itself. It's built for managing the fleet.
Got it. Fleet management. Now, we've talked a lot about automation inside the NDB UI, but, in the real world, DBAs need to plug this stuff into bigger workflows.
Oh, yeah. Like ticketing systems, ServiceNow.
Right. Or CI/CD pipelines maybe run by Ansible or Jenkins or whatever. How do we bridge NDB with those external automation tools? Provisioning, patching, cloning, but triggered from outside.
Yeah, for that real DevOps integration, the most robust and frankly common way is to use the NDB REST APIs.
The APIs.
These APIs give you programmatic access to basically all the core platform functions. So if you need to script the creation of a new database instance or decommission an old one, or maybe trigger a clone as part of an automated test workflow, you hit the REST API endpoints. It lets those external tools talk directly to NDB without anyone needing to click around in the GUI.
Makes perfect sense. REST APIs are kind of the universal language of automation these days.
Pretty much.
Okay, wow. We've covered provisioning, patching, HA, central reporting. Let's loop all the way back to the very beginning. The first administrative hurdle.
Okay, setting things up.
Yeah. When you're registering a brand new Nutanix cluster with the NDB management system for the first time, what two specific pieces of information are absolutely required to make that initial connection happen and let NDB discover the resources?
Right, the initial handshake. To register any new Nutanix cluster so NDB can manage it, you need two fundamental things for security and access. First, you need the network address for the cluster's management interface. That's the Prism Element URL or IP address.
Okay, the address.
And second, you need the credentials that have admin rights on that cluster, so the cluster administrator credentials, username and password.
Got it. Address and credentials. Without both, it just won't connect.
Nope. The registration will fail. It needs both to authenticate securely and get the rights to manage resources on that cluster.
That makes sense. Secure access to the control plane is step 0.
That's a good one to chew on.
Something to mull over until our next deep dive.